Good afternoon and welcome to the course on disaster management from IIRS. So today we will be talking about the use of space technology for forest fire monitoring and assessment and what are the recent advances in this particular technology. I am Arijit Roy and I am heading the Disaster Management Science Department at Indian Institute of Remote Sensing. So if we talk about forest fire, it's a major recurring problem and it results in loss of life, property, resources, and also creates environment which is adverse to human health. A conservative estimate by the Economy and Environment Program of Southeast Asia has actually put the cost of damage because of the South Asian forest fires at more than $4 billion US. And if we see that the past data on the forest fire frequency, there has been a significant increase in the frequency and intensity of wildfires or the forest fires across the globe. And there is a very big need for an early warning system. Basically, a sort of forest fire risk or danger index, which is based on the weather parameters at the regional level or the regional development of regional indices for better risk prediction. So if we talk about the Indian forest fires, it's mostly anthropogenic. Almost 95% of the forest fires in India are caused by humans. A number of experiments, geospatial experiments have been carried out, which actually point to this fact. So a small experiment was carried out in the erstwhile Andhra Pradesh, which at that time had both Telangana and Andhra Pradesh in it, where we basically plotted the distance of the fire location from the perimeter of the forest fire plus perimeter of the forest fire. The perimeter of the forest fire, and what we basically saw was most of the fire intensities or frequencies were within the 1 kilometer from the edge of the forest. And this is basically the distance the people who collect fuel wood go inside to collect the fuel wood. And this actually proves that the anthropogenic factors are the most important cause of forest fire. Similarly, when we plotted the distance of fire location from settlements, we observed that most of the forest fires were in the range of 2 to 3 kilometers from the settlements. And this is the average distance a herdsman or people who take their cattle to graze, the distance which they cover. Here also there is a good indication of the impact of anthropogenic activities on the fire frequencies. But this COVID-19 lockdown actually provided us a beautiful window of opportunity to understand and also to actually quantify the human activities on the forest fires, especially in the Western Himalayan region of Uttarakhand and Himachal Pradesh. So during the lockdown, what we did was that we tried to plot the fire incident, cumulative daily fire incidences from 1st of March to the mid of May of 2020. And what we observed was that for the duration during the lockdown, when no vehicular traffic was allowed on the roads and the entire country was under lockdown, the fire incidences showed a linear increase. Whereas the average cumulative daily fire count from 2006 to 2020 of the safe using the same sensor, that is a MODIS, it was observed that the increase was almost exponential after mid of April in this particular region. This has provided us a beautiful idea about how the human activities, mostly the vehicular traffic, the movement of people across the region, and the tourism sector contribute to the forest fire activities in this particular region. Because during this period, the subsistent activity like grazing, fuelwood collection, and other farming activities continued. So there was no problem, no stoppage in that particular activities of the humans. So it is basically no vehicular traffic was in this region and no tourism. So with this background, let us see what is the behind the forest fire, or what is the science behind the forest fire. See, for any fire to occur, you need the fuel, and the fuel is basically the plant material which is produced through the carbon fixation. And this plant material, when it burns, it produces the carbon dioxide, heat, and water. So if we see the fire behavior triangle, it has fuel, weather, and topography as its three sides. The amount, arrangement, and moisture of the fuel play a very, very important role in fire activities, whereas the temperature, wind, humidity, and the precipitation profiles or regimes basically define the type of fire activities in a particular region. And then the topography, there is a slope or the aspect of the land which provide us the information, or which provide us the behavior of the fire and its spread in a particular region. So if we see the fire behavior, if we plot it on time and space, a flame requires oxygen and fuel, and in presence of heat, it will burst. The fuel will burst into flame, and it's for a few seconds, covering an area of maybe a few meters. But when we talk about forest fire, it is basically the spatial arrangement of fuel, the weather in that region, and the topography, which plays an important role. And these wildfires can be there for days and cover an area more than few square kilometers, or even say tens of square kilometers in some places. But when we talk about fire regime, it is a climatic condition. It's the presence of ignitions and the vegetation type of a region, which provide annually the fuel load required for fire to occur every year. So these are the factors which define the fire regime. So when we talk about climate change, do climate change play a role in forest fire activities? Sorry. I suppose yes. The reason being, the temperatures are rising, and because of this, the snow is melting sooner, especially in the higher latitudes and the higher altitudes. And because of this, the forests are drier for a longer period of time, which provides the conditions which are prime for wildfire to ignite and spread. And an estimate has been made for the impact of the climate change as a major driver behind the growth of high frequency of western forest fires. it basically indicates that by 2050, the additional acreage which were burnt because of climate change was almost as much as of the areas which were burnt without the impact of climate change. So climate change is actually now playing a very, very important role in the forest fire activities. And it's basically because of the warming. We all know that the warming of the climate system since 1950 has been actually observed and quantified, and it is basically unprecedented. The amount of warming is unprecedented over the decades to millennia. The atmosphere has warmed, the oceans have warmed, the amount of snow and ice have diminished. And this all is because of the concentration of the greenhouse gases. And you can see on the right bottom side, the observed changes in the surface temperature for the last century. Many of the areas have shown an average increase of temperature of more than 2 degrees centigrade. So, because of the climate change, what is happening is that there is a perceptible change in the soil moisture. And almost all of the climate models have actually projected these scenarios, that the drought-like situation is going to increase, especially in the regions like Europe, the Brazilian rainforest, the breadbasket of US, the Indo-Gangetic plains. So these areas are vulnerable to drought-like situations. And to couple that, the number of dry days is also increasing. Although precipitation may not be changing much, but the extreme rainfall events are increasing. So that even if the total precipitation is there, the precipitation is extreme in a few days. So you have the flood-like situations, and you also have the increase in number of dry days, which actually translates to the drought-like situation. And all have basically been used in various models and seen that large global forest fire increase, especially at 1.8 degrees centigrade warming. Many of the areas which are covered by forests are expected to have almost more than 1,000 times the fire frequencies. So you can see the areas in the central Indian region, in the southern part of the Amazon, and also in parts of Kenya, Tanzania, and that region. They are expected to have a fire frequency of more than 1,000 times the baseline global mean, that is from 1850. So with this background, let us see how temperature regime plays a role in the fire occurrences, especially in India. So on the left, you see the average temperature regime of the fire season, that is from January to June. And on the right, we have the corresponding fire counts from MODIS. This is for 2016. So we have been doing this every year as an exercise. So you can see that during January, the southern part of the country is hot. And you have fire activities in the Nilgiris and the southern western Ghats. By February, more of the area in the southern hemisphere, southern part of the Indian subcontinent warms up, and you have fire activities in this mostly concentrated in the western Ghats and the eastern Ghats and some part of the Deccan Peninsula. You also see that there are a lot of fires in the northeast region, but it's mostly because of the June cultivation. Then during March, almost the entire subcontinent is hot, and you have fire activities across the country. April, most of the fuel in the southern part of the Indian subcontinent has burnt off. So you have the forest fires in the central part and in the northwestern India, that is the Himalayan region. By May, most of the fuel has burnt off. So, but still, the Himalayan region are getting warmed up, and you have the fire activities in those regions. With the onset of monsoon in June, most of the fire activities across the country stops. So if you see a snapshot of the hotspots of forest fires across the globe, you can just see during the April 21st to 27th of 2021, this is how the fire activities look like. You have extensive fire in the South Asian region, the Indian subcontinent. You have fires in the African savanna, the Central African forests, parts of Mexico, USA, also in the northern latitude, especially in the Caucasus region and the Russian Federation. So this entire thing basically reverses during the autumn. That is during October. So before we go further, I'll just briefly talk about the Sendai framework. So basically, Sendai framework is the result of the meetings at Sendai for charting out the targets and the way forward for the global community to counter the various impacts of disasters up to 2030. So in the Sendai framework, 7 targets were set, basically to reduce the mortality, reduce the impact of disasters, reduce the effect of disasters to the communities, and also improve the various early warning systems, knowledge sharing and other things. And to achieve that, basically 4 priorities of action were identified. That is to understand the disaster risk, which basically translates to the physical basis of disasters, the science behind the disasters. Then investing in disaster risk reduction for resilience, both infrastructure, that is basically creating infrastructure, both space-based and ground-based. Then strengthening disaster risk governance to manage the disaster risk. That is to, when we talk about governance, it's basically availability of information, timely information. So basically it translates to development and dissemination of information. And then enhancing disaster preparedness for effective response, and its recovery, rehabilitation, and reconstruction, which basically translates to a robust early warning system and logistics. So basically it emphasizes on enhancing early warning system, dissemination of information, and to do that, create a sensor web for real-time information retrieval and processing, which will help us from just estimating disaster loss to identifying the disaster risk for effective disaster risk management. So when we talk about forest fires, there are basically 4 types of forest fires. That is creeping fire, ground fire, surface fire, and crown fire. Creeping fire are mostly in the higher latitudes, especially in the northern hemisphere, where you have a lot of duff. There's a semi-decomposed organic matter. Because of the very cold condition, the decomposition is not fast. And you have a very thick layer of duff there. So when the fire ignites in this stuff, it basically is underground, and only in some places you have the flame and smoke coming out from the duff. Then you have the ground fire, which is the most common forest fire in India, which impacts the herbaceous vegetation, the dead and decaying litter, and the trees and logs. Then you have the surface fire, which is a very devastating forest fire, and mostly this is there in the African savanna. So the entire savanna basically burns out, and this is very, very detrimental for the wildlife. And the most devastating type of forest fire is the crown fire, where the entire forest, especially the crowns, they start burning. And this is mostly prevalent in the coniferous forest, which have a high resin content. So you have this type of forest fires in the California region. So when we talk about the use of space technology for forest fire management, there are a number of sensors for monitoring the forest fire. But when we talk about the geoinformatic input, there are a few parameters where the contribution of remote sensing is huge, like burnt area mapping, burnt area progression, or even identification of active fire location. Here, the remote sensing contributes more than 90% of the inputs. Whereas the other aspects like fire proneness assessment, fire spread models, or ecological damage assessment has to have a significant contribution from the meteorological sensors as well as the ground-based inputs. So if we talk about the remote sensing sensors available for monitoring the forest fires, we have a plethora of sensors like NOVA, VHRR, MODIS, SPOT, ASTER. So for active fire identification, we need basically the thermal sensors, which are there on MODIS, which are there on ASTER, which are there on SNPP, VIRIS, or NOVA. But for assessing the burnt area, we need a multispectral satellite data which have the SWIR band, then the shortwave infrared band. And here we have the IIRS AWIVS, Landsat TM, LIS3, Sentinel-2. There are a number of sensors which are available. So we will talk about the use of geoinformatics for forest fire management by one. That is, first we will be talking about the monitoring aspect, then we'll be talking about the early warning or risk analysis assessment, and finally the spread models. So when we talk about the forest fire monitoring, that is mainly the active fires. So here we have the two sensors, that is moderate resolution imaging spectroradiometer, which is on board NASA, Terra, and Aqua satellite. So these have a thermal band, and using the version 4 contextual algorithm developed by Giglio and his team, regular monitoring of the forest fire across the globe is carried out by this particular sensor. So MODIS is now almost 20 years old. So as a replacement, and also for continuity of the data, we also have the SNPP VIIRS data, which is basically a visible infrared imaging radiometer suite, and was launched aboard the Xiaomi National Polar Orbiting Partnership satellite, SNPP. And we have two pairs of satellite having the same radiometer suites on board. That is, one was launched on October 28, 2011, and another was launched in January 18th of 2012. And this carries two separate sets of multispectral channel and provides the full global coverage at 375 meters and 715 meters every 12 hours or less, depending on the latitude. It uses the same algorithm to generate the active fires, and it generates active fire at two resolutions, that is at 750 meters and at 350 meters. 375 meters, sorry. So for identification of active fire location, it basically depends on the extent of the burning, the flame by smoke ratio, the background characteristic of the location, the atmospheric interference, and sensor saturation. So basically what is required is a region-specific customized package, and simply providing an active fire location doesn't suit the purpose. So it also needs to be told at which location, which beat, which bound, which compartment, which division the fire is active. And this has to be transmitted to the stakeholders. In this case, in India, the forest departments in real time for utilization. So this is how the thermal anomaly is basically detected. It basically detects the thermal anomaly is basically the pixel which has a brighter thermal reflectance than the surrounding area. And these pixels are picked up especially inside the forested region and are flat. So while this was being carried out, the entire algorithm was being developed for Indian scenario at NRSC. So two teams were there. One team was there in the lab, which was analyzing the MODIS data. Another team was there in the ground, of which I was a part of it. And on that day, on 14th March of 2005, when the thermal signature was detected by the MODIS Terra satellite sensor, this information was relayed to us on the ground, and we basically went to the location to see whether actually it is burning or not. And this is what you see in the feed. So we got the images and got the locations, and we verified this entire thing in the field. And based on the extensive ground truthing, the algorithm was finalized. So when we talk about the forest fire monitoring using satellite data, we have the data from MODIS, we have the data from SNPP-VIRIS. And apart from these two, we also have data. We also can monitor using geostationary satellites like GEOS, Himawari, or INSAT 3D, 3DR. So in the couple of slides, I will show you how the geostationary satellites can also be used for monitoring forest fire. But in this slide, I am just displaying how the MODIS fires and SNPP-VIRIS fires are detected using the two sensors. But since SNPP-VIRIS has a higher resolution, so the smaller fires can also be picked up. So the number of fires you see in SNPP-VIRIS, which is on the right side, is much higher than that of MODIS, and it's basically because of the resolution of the satellite. So now we talk about the forest fire monitoring using geostationary satellite data. The plus point of using geostationary satellite data is that it can image the disk which it's staring at once every half an hour. So using a combination of INSAT 3D and 3DR, we can basically image the disk every 15 minutes. And in the INSAT 3D, 3DR, we have two channels, that is the channel band 3 and band 5, which provide us the information on the thermal signature from the ground. But the problem is that these sensors, since they are at a height of 36,000 kilometers above Earth, the resolution of the sensors is very, very less. So there's basically 4 kilometers is the resolution of the sensors. And these two bands are used for different types of fires. So basically the thermal infrared 1 sensor, that's the band 5, is detects the temperature which are more than 300 Kelvin, and the MIR band, which basically identifies the objects radiating at temperature of 800 Kelvin. This is basically the temperature of the burning grass. So if you see the spectral distribution curve, so you can see that as the temperature increases, the maxima shifts toward the shorter wavelength, basically the Wien's displacement law, and it basically gives a peak emission of radiance of a back body, which is at 3.9 micrometer, which is the band 3 of the INSAT channel. So using this, we are able to provide a hypertemporal fire detection over a particular region. So this sort of sensors can provide us information of how long a particular fire event has occurred. So during 2016 fire event of Uttarakhand, the INSAT 3D 3DR could detect a fire almost 27 times at one particular location. So if we divide 27 by say 2, it comes to something like 13.5 hours, 13 hours and 30 minutes. So one of the fire was there for that much time. Whereas the MODIS, it passes only twice a day. So we basically miss out on the many of the fires. So next part of the monitoring is the burnt area mapping. Here, the shortwave infrared band is basically used to remove the smoke from the region, from the burnt area, for better mapping. And this particular thing also band also ensures the spectral separability of the forest fire scars. So digital extraction and automation is also possible. So how do we detect this? So the top row of images is the false color composite using shortwave infrared, near infrared, and red after fire event, and the middle row is the same area before the fire event. So you can see the burnt areas are spectrally very, very distinct from the unburnt area, and this can be picked out very easily using digital image processing. And using this, we could estimate the fire affected area in the region. For this, for basically monitoring this, extensive ground truthing was done. And presently we have the Sentinel-2 data, which is also very good for burnt area mapping. So you see, this is a part of the Nainital district of Uttarakhand where fire has occurred. Here, because of the smoke, we are not able to see what is there, but moment we use the shortwave infrared, we are able to see the actual fire as well as the burnt areas in this region. So you can see all these are the burnt areas. Now, if we zoom any one of these regions, you can identify the area which has burnt. So all these dark blue region are the areas which are burnt, and this is the active fire which is there along the fringes. Another region which has zoomed. We can also use this information for monitoring the impact on the ecosystem processes and ecosystem structure like the biodiversity. So using the biological richness map, which reflect the vegetation uniqueness and complexity, the biodiversity value, and the level of disturbance, we are able to identify how much of the area which has been burnt falls under high biological richness or how much is in the moderate biological richness. We have done this for a small area, that's the Rajaji Tiger Reserve. But basically what happens is that due to the ground fire, the biodiversity is affected in the form of impact on the seedling and sapling, mainly the regeneration potential, the herbs and shrubs which harbor most of the medicinal species, the smaller animals and insects which are important in maintaining the ecosystem processes, and other like fauna like herpetofauna, etc. But the fire also impacts the air quality, and we are able to monitor the high aerosol concentration because of the fire activities, mainly the smoke, mainly the particulate matter 2.5 or PM10. They can be detected using the satellite data like MODIS. Apart from this, we have other data like atmospheric infrared sounder from Aqua, which can detect the carbon monoxide concentration, again as a result of fire activities. And since carbon monoxide is heavier than air, These particular gaseous components tend to accumulate in the valleys, and they are a serious health hazard for the people in that region. Then the distribution of the tropospheric columnar nitrogen dioxide. This can also be detected using the ozone monitoring instrument like Aura and the others. Then basically these fires, they cause a lot of carbon dioxide emissions across the world. So a number of studies have been carried out to assess the annual CO2 emissions caused by various forest fires. So after we talked about monitoring, let us talk about the risks and vulnerability. So if we want to identify the risk and vulnerability, a very simple method is to identify the forest fires frequency or map the forest fire frequency. And this we carried out using the daily MODIS and SNPP various data on a grid size of 5 km by 5 km across Uttarakhand. And we identified areas where over the last 20 years, the number of or the frequency of fires in that particular region is as high as 30 times. So this can give a very, very rough idea about the areas which are vulnerable to frequent forest fire. But this is not enough. What we need is an early warning system, or basically a system to identify the forest fire risk. So we generated or developed a fire danger rating system. It's a decision support system which involves factors which influence the fire danger. And this fire danger index is indexed into different classes of fire danger, that is low, moderate, high, very high for rapid characterization, so that it can be used for implementing the mitigation measures for controlling the fire. So this particular fire danger rating system has two biophysical components. One is the dynamic index, which is based on weather parameters like air temperature, relative humidity, wind speed, and rainfall. The other one is a static index based on constant parameters like fuel characteristic, topographic condition, vegetation type, and edaphic condition. And this is then integrated to provide the fire danger rating. Presently, this model is calibrated for Western Himalayan region of India. And the parameters which are used for this particular index are the weather conditions like air temperature, relative humidity, wind speed and direction, previous day's rainfall, precipitation, the dew point temperature, air temperature, the potential evapotranspiration, the land surface temperature, the entire gambit. And then as static parameters, we have the forest type, slope, aspect, elevation, the NDVI of the previous 6 months, enhanced vegetation index, the albedo, the terrain ruggedness, the road, rail and network and human settlements, the population density, and the calorific value of the fuels in the particular vegetation type. The calorific value of the live fuel, dead fuel, as well as the litter. So the fire danger index are basically the two components. One on the left side, you have the static component, on the right, you have the dynamic component, which are integrated by a generalized additive model to provide the finite fire danger index. And this has an accuracy ranging between 86% to 92% with respect to actual fire occurrence. So these are the fire danger maps overlaid with fire points. The accuracy was computed for each day, assuming that the fire fell in no fire, low fire, and moderate fire regions as unidentified fire pixels by the forest fire danger index. So you see the accuracy. So the accuracy is significant in that region, and this entire process has been now automated. And since this product is dynamic and needs to be run daily, so what we are doing is that the system now downloads the satellite data, processes it, and then it computes all the indices, integrates the two indexes, static and dynamic indexes, and provides the forest danger index, and then it publishes it on the website. So this is the automated forest fire risk advisory and monitoring system which we have developed, and provides the information on the fire activities on a daily basis. So this is the type of information we generate, the high risk areas. And it's not just providing it as a form of a map, but also sending an SMS to the stakeholders as advisories. So we also have developed a mobile-based app for forest fire reporting and monitoring, which include a geospatial solution, which consists of an Android mobile app and a web-based dashboard. It has been shared with the Jammu and Kashmir Forest Department, Uttarakhand Forest Department, and also for the Mexican Forest Department. And this provides this helps to provide the near real-time surveillance during active fires. And this mobile app allows for geotagging of forest fires along with field information and the type of other informations like the forest type, the cause of fire, the type of fire, the affected species in the area, the topography, accessibility, etc. So this is basically a demonstration of the power of geospatial technology for monitoring the fire activities, especially by the decision makers. So this is basically a digital fly-through created during 2018 fire events from Uttarakhand. So you can see the fires which are here. So these are the smoke, and this is a fire, and the dark burnt areas are being, you can also see here. I'll just point it out when we come here. So you see these are the areas which has been burnt. So these are the burnt areas. All these blue areas which you see are the burnt areas. And this provides us critical information about the extent of fire and other impacts which are caused as a result of wildfire in a particular region. And this is done using open source tools, open source data, and open source visualization software. So after this, we come to some of the advanced modeling approaches. Basically, this is the exercise where the forest fire spread was modeled using various geospatial tools and techniques. So this basically uses three components. One is the data. Second is the connectivity. And third is the movement of fire across the landscape based on the connectivity and the directions. So for generating the connectivity, we use the complex network algorithm. That's basically the graph theory for estimating the functional connectivity. And once the functional connectivity was established, we used the fire spread, developed a fire spread model. So this fire spread basically depends on the availability of the fuel, the meteorological conditions like wind, speed and direction, temperature, humidity profile, connectivity, etc. And the use of the meteorological conditions was basically taken from the WRF model, that is based the data on temperature and wind. And we also have the inputs from MOSTAC and IMS, Indian Meteorological Service. So the meteorological data was put into the fire spread model, and using cellular automata, we generated the the spread of the model using the neighborhood impacts. So I'll just show you the model output. So this is an experiment which we did in a part of Corbett National Park during 25th of April 2016. So I will just zoom on to that. Every iteration here is a time step of half an hour. So every half an hour, how the forest fire is spreading in that particular region is being simulated here. So you see that over the 24 hours, the entire region was affected by fire and was was basically monitored using satellite data. So after 24 hours, we identified, so it will go on till the 48th iteration, you will just see it. So after the 48th iteration, this was the fire spread. And when we assessed it with the actual burnt scar using high resolution satellite data of Sentinel-2. So what you see is the area, black one are the areas which has been simulated as the area where the fire will spread, but it has not spread to that areas. Whereas the red one is the actual burnt areas of the pixel. So you can see it is able to simulate the spatio-temporal distribution or spatio-temporal spread of the fire in that particular region. And this information is very critical for the management, because then they will be able to inform the ground people about the direction of the fire spread, as well as the direction from where they will be most effective in preventing the spread of fire. All these activities which I showed you are accompanied by extensive ground truthing, and me and my team has been going to the forest, especially the burnt areas where the fire impacted areas, and we have validated all these modeled outputs from the ground. So presently we have developed a forest fire danger index. We have developed the spread models. We are developing the back propagation algorithms. We also need to develop human activity index, and all of them have to be integrated to provide the real-time data reception and model output. So for this, we need a sensor web, which can help us in decision support, developing a decision support system. But this cannot be done by one organization alone. Here, we need information from the space-based communities, especially for information as well as communication, and also from the government departments in terms of ground-based observations. And we need the help of the analysis group, especially the academia, the research institute, and organizations like ISRO, to provide us a real-time spatial decision support system, which will ensure effective disaster risk management for forest fires. Thank you very much.